Enthalpy is given by the letter H, and it's the sum of internal energy plus pressure multiplied by volume. They just found that they were using it so often that they just made up a new property that is formed from other intensive properties. And so we have a new one. Specific values are given on a mass basis. So small letter h enthalpy equals capital H enthalpy divided by mass. Or likewise, enthalpy equals H times N. So if I have the specific enthalpy and I know the mass of the system, then I can find the enthalpy of the system, where the small letter is an intensive property and then the capital letter is an extensive property. It's of the whole system. Okay, so we talked about quality. We know that that is how we find where we are if we are in the dome here, and we know that we're someplace between this point F and this point G. We know we're in there somewhere. We know that temperature and pressure are not independent of each other, and we need another variable. And so we use something called quality. And quality is given by the formula. We use the symbol X to represent quality. And it's equal to the mass of the vapor in the system divided by the total mass of the system, or mass of the liquid plus mass of the vapor. And that's what X is. We have these other formulas that give us V equals 1 minus X times VF. Again, VF is the specific volume at the saturated liquid point, plus X, which is quality, times the VG, which is specific volume at the saturated vapor point over on the other side of the graph. And they just rearrange it here to distribute that VF, and we end up with this. We can also rewrite this so that we have, and solve for X with this. So X equals V minus VF divided by VG minus VF. So if we're given a specific volume, and we can look up on our tables the saturated specific volume and the saturated liquid specific volume and the saturated vapor liquid or specific volume, so the VF and the VG, we can look those up on a table. And if we're given another specific volume, then we can find X using that. And likewise, we can use if we're given internal energy, we can use that, UG minus UF, or X equals H minus HF over HG minus HF. On the tables, because it's used a lot, they have this extra value for enthalpy here. So this is HFG, and it equals, these two are the same. So the HG minus HF is HFG, given on the tables in the book. We'll see later that we can do this also for entropy, but we haven't got there yet. Specific heats are other values like enthalpy are related to internal energy. We call them specific heats because under certain conditions they relate to temperature change of the system, and they relate temperature change of the system to the amount of energy added by heat transfer. Generally, when we have heat transfer, it is not related to temperature, and a big mistake students make is to relate heat transfer, which Q, to temperature, because they're just different concepts. But here, specific heats are related, and they're particularly useful when we get to the ideal gas model. They're intensive properties, and they're defined for simple compressible substances by the partial derivative of the functions. So our functions of internal energy and enthalpy are functions of temperature and pressure. And so we use a partial derivative, which means, if we look at it here, CV is the partial derivative. That's what this symbol, this is partial derivative. So instead of derivative, we use partial derivative. And what the partial derivative means that is that we hold, we fix the whatever's here. So we're fixing the volume, the specific volume, and we're taking the derivative of U with respect to temperature. And here, with this one, we are fixing pressure. So we're holding pressure in the enthalpy calculation. We're holding pressure as if it's constant or fixed, and then we take the derivative of H with respect to temperature. So that is the specific heats, and they, again, are tabulated values that we can use. We have the specific heat ratio here, which is the ratio of those two.